Hey folks, I had a question from one of the students and I wanted to actually go through this. This is a good example of something that we can use where we're using the principles of working with minimization and maximization, that is taking the derivative, setting it equal to zero, that sort of thing, using our critical points. And it should look very familiar from the standpoint of we're really going to use more calculus one stuff along with parametrization for it. So we're going to be finding the distance between a point and a line using derivatives. So where we're going to start out now, I'm going to grab my highlighter. And there we go. I want to find the distance, right, between the point and the line. So the line that I have here is this line, which is negative 4x plus 7y plus 2 equals 0. And I want to find the point closest to 2, negative 4. So the first thing that we need to do is we need to figure out what is the thing that we're actually going to be minimizing. Now we're minimizing distance. And so consequently, we need a function for distance, and that's the distance formula. And so we've got distance, and the distance from any point to the point 2, negative 4 is going to be the square root of x minus 2 squared plus y plus 4 squared. Okay, and that's what we've got right here. Okay, and that's just your standard distance formula. We should know that. That's definitely something you should have memorized. It's the Pythagorean theorem. Next up, what we're going to do is we're actually going to parameterize this to get it to a function of a single variable. And then once we parameterize it to get it to a function of the single variable, then we'll go in and we'll take its derivative and set it equal to 0. The reason why we want to do this is because if we went in and say, for example, took the partial with respect to x and the partial with respect to y for d, all we get is we'd get x and y, then we'd have to plug in the parameters anyways. And you could possibly do that. Well, you get like x equals 2, y equals 4, okay? Y equals x equals 2, y equals negative 4, excuse me, which would work, but you get all sorts of problems where things like zero out, and you've got all sorts of issues here. The easiest thing for us to do is just use our parameterization skills and then go in and set the derivative equal to 0. So that's what I did. I let x equal t, and then y, I used my equation here in order to figure out what y was, and y ended up equaling 4/7 t minus 2/7. And the algebra is there, and you can take a look at that if you want to pause it. Now I plug that back into my distance formula here. So I got my distance formula, and then I went in and I utilized some algebra in order to simplify this whole thing. Okay, I took the square root of 49, that gives me 1/7, and then I went in, and this here, okay, is actually the derivative, and I should point that out. I went out and I took the derivative, so I got d dx, okay, of this whole thing is equal to now 1/7 times 65t over plus 6 divided by that square root, okay, which fairly simple. I mean, from the standpoint of you're just going to use a quotient rule here. Now what I need to do is I just need to go in and I need to figure out when does this equal 0. Now, the bottom part can't equal 0, so not 0. The top part, so 65t plus 6, that's got to equal 0. And then we'll go in and we'll check and make sure that that doesn't actually make the bottom equal 0 as well, because then you'd have a problem. You'd actually have a critical point, but you wouldn't actually have your derivative equal to 0. There could be some issues there. So we went in, we did exactly that, and when I did that, I got t equal to negative 6 over 65. Now I did a couple other things here, and I'm going to show you just for a second. If I wanted to find the distance, what I could do is I could then just plug in t, plug in negative 6 over 65 into the distance formula here, okay? And then that gave me 34 over the square root of 65, and that's actually what the distance was. But the problem wasn't actually asking me for the distance, it was asking me for the point on the line that had the minimum distance. So I have to go back to my parameterization. I'm going to go back to my parameterization. X was equal to t, remember? So we've got negative 6 over 65 here. And then y, I just plug in t into the equation that I have for y. And what I get is I get negative 22 over 65. And again, this is just kind of plug and chug, a little bit of algebra. So your big points here as we're doing this one is 1, okay, what you're going to do is you need the distance formula. You need an actual formula in order to minimize, right? And that's a principle for minimization that you should kind of remember too. Anytime I need to minimize anything, I've got to start out with what am I minimizing? Create an equation for that. 2, okay, I want to go in and I parameterize x and y. And then 3, I'm going to sub the parameterization into the distance formula. Fourth, okay, set the derivative equal to 0. And so when I set the derivative equal to 0, right, that ends up giving me t. So 5, I've got to plug in t to the parameterization. And this is a good example of how to go about figuring out problems of this kind, right? Big idea. What you're going to do is you need the equation that you're going to actually go in and you need the equation that you're going to go minimize, all right? And that should be in terms of the variables that you're going to be solving for, right? Utilizing the information that you're given, that sort of thing. Distance formula, that's pretty common. That's a common thing that we're going to go out and minimize. It actually shows up quite a lot. We want to be able to parameterize, okay? And then inevitably, you're going to take the derivative and set it equal to 0 in order to find your critical points in order to then go in and find your minimization.